Hey everyone, so in this video I'm going to go over some more independence problems. This is Independence Day 2, so there are different rules that apply in here, but mostly they are the same. The do now talks about whether or not events are independent. Now remember, an event is independent if one event does not affect the outcome of the others. So one event happening first will not affect the outcome of the event happening second. So the first question says you flip a coin and then you roll a fair six-sided die. The coin lands heads up and the die shows 1. So are these events independent? Which means that does flipping the coin first affect rolling the die second? And the answer to that would be no. So therefore these events would be independent because the idea of flipping a coin and rolling a die would not affect one another. So let me just put this in the right spot. So independent. The next one says a bag contains 8 red marbles and 4 blue marbles. You randomly pick a marble and then pick a second marble without returning the marble to the bag. The first marble is red and the second marble is blue. Now here's the deal. You pick a marble and then you picked a second marble, but you did not return it to the bag. Whenever you see something without replacement, those events are not independent because what's happening is when you take that marble out, that first marble out, you change the probability of getting the second marble. The reason why is because you're taking away from the bag. So say there are 10 marbles in I say right here, 8 and 4. So 8 and 4 would make 12. So if you take out a marble and the first marble is red, that would mean that you have 8 out of 12. And then you'd pick a second marble without returning the marble to the bag. That second marble was blue. Well, that would mean there are 4 blues, but you took a red. So that means the total is not 12 anymore, it's 11. So that's what we mean when events are not independent. So the first event affected the probability of the second event because now the bottom is 11 and not 12 because there's no longer 12 in the full bag. And that's what we mean when we decide if events are independent. Now, the example 1 is actually just like what we've been dealing with the table. This is independence with the table. We are going to go over in this lesson independence without a table. But let's go over this one. Here are your formulas. This is the one I like to use. They're both the same. They're just different with the letters, if you notice. The key thing that you should notice with the formula is that whatever letter is here is the letter that's before that bar. And the same thing here. Okay. So they give you a table about being an Amazon Prime member and not an Amazon Prime member and being a college student and not a college student. So if you wanted to label it, I would label probably Amazon Prime as A, this is A Prime, and we can make this student and not a college student. We'll do S Prime. That means not. Okay. So it says, are the events student and Amazon Prime member independent? Show your work and justify your answers using appropriate numerical probabilities. So you always have to think about what should come first. I think that becoming a student probably would come first, but it really doesn't matter. So let's see if being a Amazon Prime member would be affected if you were an Amazon Prime member given you were a student first. So again, I'm making sure that these letters are the same. And what we're trying to see is that if this is equal to this with a condition on top of it. Because if they're equal with this specific condition on top of it, they are independent. So the probability of being an Amazon Prime member, well, that means all the people who are Amazon Prime members. There are 60 out of 250 people that are Amazon Prime members. Now, if you remember the trick from my previous video, that means that we are either going to divide by 40 over 100 or 20 over 150 because that's the same placement as 60 over 250. But using the formula, you have an Amazon Prime member given you're not a college student. So also I could have made this S. It doesn't really matter. So what that means is I'm going to take from here, because that's my condition, which is what I was saying. It would be 20 over 150 because A is 20 out of the not student 150. So now I'm going to see if these are independent by dividing them. So I'm going to do 20 divided by 250 in my calculator. And I end up getting 0.08. And I'm going to see if 20, oh, that was silly. 60 divided by 250, sorry. That's 0.24. So let me just fix this one. I did that one backwards. Okay, 0.24. And then 20, let me just make sure that's clear. 20 divided by 150, 0.133, repeating. So these are not equal, so therefore these are dependent or not independent, whatever you would prefer. Okay, so I'm skipping around here, but the reason why is because the previous lesson really went over the table independence, so if you want more help on that, just go rewatch that video. But there is a new rule that we want to look over today in this video, and that's the independence rule with and. So the rule of thumb is if you see the word and, you're going to want to multiply. So if you see and, we multiply. And that's kind of similar to when you guys see the word or, we add. Now the reason why this rule right here is all the way behind all the other probability rules. If you remember at the beginning of probability, we had a whole lesson on like all the different rules. And the reason why this one is here is because you cannot use the and rule unless the events are independent. If the events are not independent, you cannot assume that this works. So if you remember in the do now, we talked about how to determine events are independent, like just by logic. And then the other way you can determine an event is independent is if they straight up just say the events are independent. But this is a nice rule. It's pretty easy to use. It's just multiplication. So the first question says determine if A and B are independent. Well, if A and B are independent, that means that the probability of A and B, oops, I just wrote the word and, hold on. That means that the probability of A and B would equal to their product. Probability of B times, oops, it really doesn't matter, right? It should just be the probability of A if I was going in order. Probability of A times the probability of B. So the probability of A and B is 2 out of 25. They tell us that right here. And the probability of A is 2 out of 5. We multiply that by 1/5. So that would get me 2 out of 25. And that is equal to that. So therefore these events are independent. Next one, same deal. So I'm going to do are these events independent? So I'm going to use my rule. Are they equal to the product? I don't know why I keep writing B first, but whatever. I'll just leave it. Okay, so remember they're commutative, so it doesn't really matter what I write first. So this is 1 out of 25. That would equal, what's the probability of B? 1/4 times the probability of A, that's 2/5. That would be 2 out of 20. And that does not equal 1 out of 25. So we would say not independent. Okay, this is where this rule really comes into play. This question kind of gets us there. On a given school day, the probability that Nick oversleeps is 48%. So the probability that he oversleeps is, remember you always want to change this to a decimal, 0.48. The probability that he has a pop quiz is 0.25. So I'll make that P. Pop quiz is 0.25. Assuming these events are independent, and this is the phrase you want to look for. These two events are independent, assuming they're independent. Which should make sense because whether or not he oversleeps and whether or not he has a pop quiz should not really affect each other. The teacher doesn't really know that he overslept and then says, oh, I'm going to give a pop quiz today. So these events should be independent. What's the probability that he oversleeps and has a pop quiz? Once you see that word and you see that you're assuming these events are independent, that means you can multiply the events. So that means I'm going to multiply 0.48 times 0.25, and that gets me 0.12, and as a percent, that's 12%. Okay. All right, so this is a spinner question. Spinner questions are great. We can use them and assume that the events are independent because when you make one spin, it's independent of making a second spin, meaning that the first spin will never affect the spin of the second. This is not a trick spinner. So therefore, we can use the multiplication rule of independence. So this is an example where you don't have to see the word the events are independent because this is a type of situation where you would assume the events are independent because spinning one spin does not affect the spin of the second spin. Now, I do want to make you aware that this is not really in proper proportion. Like, do you see how this one is split, the one I just pointed an arrow with? So really, we could split all of these guys and make them like this would make it 1, 2, 3, 4, 5, 6, 7, 8 pieces. Okay. So we're going to do the probability of red and then green. We see the word and, we're going to multiply. So red, well, that means that we have 1, 2, 3 pieces out of 8. So that would be 3/8. And then green, there's only 1/8 out of there. So that would be 1/8. And if I multiply this out, I would end up getting 3 out of 64, and that's my probability. Okay, green and green. So I see and, so that would be multiplication, and that would be 1/8 times 1/8, which gets me 1 out of 64, because there's only 1 out of 8. Okay, blue and blue. Well, blue, if you notice, is actually pretty much half of the spinner down there. So I'm going to do 1/2 times 1/2. That gets me 1/4. This one says yellow and then blue. There's no yellow on the spinner at all, so that's 0. Okay, so if you remember in the do now we talked about with and without replacement, and you can still multiply with and without replacement as long as you account for the fact of not replacing. So if you remember in the do now, I took away from the denominator. So I'm going to do that again here. So this is a bag that contains 12 red and 12 blue and 12 green M&Ms. The first M&M is drawn and it's looked at and eaten. Find the probability that these events happen. So 2 red M&Ms are chosen. If you say this out loud, that means you're going to choose a red. Oh, I guess I should use the color red. That would make sense, right? That means you're going to choose a red and a red. When you say that word and you think about what your probability is, you know multiplication, okay? So there are 12 reds in the bag out of how many? 12 plus 12 plus 12, that is 36 M&Ms. Now here's the deal. You can use the multiplication rule because it's and, if you account for the fact that you are going to take away a red because you're eating it. So if I eat a red M&M, that means that there's 11 left. And if I eat a red M&M, that means the whole bag has one less, so that would be 35. And when you multiply that, you get 132 out of 1260, or you can reduce it to 11 out of 105. Okay. Next question. A red and then a blue are chosen. So that means a green and then a blue are chosen. So I'm going to take a green, which is 12 out of 36. And then I'm going to take a blue, which is also 12, but we ate a green. So that means that there's 35 in total. Sorry, I guess I should keep this same color. So the 12 didn't change because I ate a green, not a blue. And then I would get the answer of 144 over 1260. Okay. This is the same idea. The only problem here is that there's either order, which means either thing can happen. So we're actually going to do this twice. So we're going to get a red and a blue, which means that we have 12 out of 36 times 12 out of 35. Or, remember when we say the word or, we add. You could have a blue first, 12 out of 36, and a red, 12 out of 35. Okay? And you would multiply these guys together and get 8 out of 35. Okay, I'm going to go over one more question in this video. The last question is done in Miss Tribby's video, so if you want to skip to her last question for the bottom one. So we have here, recall that 2 events are independent if the probability does not change the probability of another one occurring. These are your formulas for independence, all of these guys, including the and one that we just went over today. So you have a credit card company that states 42% of its cardholders are classified as long-term cardholders. So L would equal 0.42. And then they say 35% pay their bills in full each month. So I'll make that F. 0.35. And 23% are long-term cardholders who also pay their bills in full. So that means you're a long-term cardholder and you pay your bill in full. So that's 0.23. Let the event that are randomly selected be L and F and okay. Are the events independent? So the easiest way to prove that they're independent with a problem like this is to see if the multiplication rule happens. So L and F, if they were independent, would be the product of L times the product of F. Okay, so L and F is 0.23. Would that equal multiplying 0.42? Oh, I don't know why I wrote 5. Sorry. 0.42 times 0.35. When you multiply that in your calculator, you actually get a 0.147. That is not equal to 0.23. So are these events independent? No. And you would say because the probability of L and F does not equal the probability of L times the probability of F. And that's really it. And if you would like to go over number 8, well, actually this should be number 10, my bad, just go over to Miss Tribby's video, which I also posted. I hope you have a good day, and I'll see you soon.